Okay. Hi everyone, welcome back to this video series on Windows Server 2016, networking with Windows Server 2016. As we have been discussing so far in this book, servers are the tree trunks of our networks. They are the backbone infrastructure that enable us to get work done. If servers are the trunks, then the networks themselves must be the roots. Your network is the infrastructure that supports the company infrastructure. It makes up the channels which any and all devices inside your company use to communicate with each other. Traditionally, there have been server guys and network guys in the IT profession, and in many places that is still the case today. An administrator who primarily works on servers does not generally have enough time in the day to also support the network infrastructure in an organization of any large size. And the reverse is also true. Network administrators generally stick to their own equipment and management tools and wouldn't be interested in diving too deeply into the Windows Server world. However, many of us work in smaller companies where many hats must be worn. Some days, both the server and the network admin hats sit on top of each other. And so we must understand at least a baseline of networking and tools that we can use to troubleshoot connections that are not working. In addition to that, Windows Server 2016 brings a new networking mindset into focus, the virtualization of your networks. There will always be some semblance of a physical network using physical switches and routers to move the packets around between different rooms and buildings. But now we are also incorporating the idea of software-defined networking into our Windows servers, which gives us the capability to virtualize some of that configuration. Not only the config itself, we are actually virtualizing the network traffic and building our networks from within a server console rather than command line interface to configure our router, which was always needed in the past. I am getting ahead of myself. First, let's talk about some of the new and useful things inside Windows Server 2016 that do not involve working on physical networks or any networks, I suppose, because they are going to be important for any administrator in today's networking world. Later, we will take a few moments to further explore this new idea of network virtualization. Here are some of the items we plan to discuss today. Intro into IPv6, networking toolbox, building a routing table, software-defined networking. Intro to IPv6. Welcome to the dark side. Unfortunately, that is what many people think of IPv6 at the moment, while IPv6 is by no means a new thing. In my experience, it is still something that almost no one has deployed in their own networks, In working with hundreds of different companies all over the world over the past 2 years, I have only found one organization that was running IPv6 over their entire production network, and it wasn't even true native IPv6. Instead, they were tunneling. Instead, they were using a tunneling technology called ISATAP over their whole network in order to make all of the servers and clients talk to each other using IPv6 packets, but these packets were still traversing an IPv4 physical network. Why does it seem to be so difficult to put IPv6 into place? Because we have been using IPv4 since basically the beginning of time. It's what we all know and understand, and there really isn't a great need to move to IPv6 inside our networks. Wait a minute. I thought there was a big scare being pushed about running out of IPv4 addresses. Yes, that is true for IP addresses on the public internet, but has nothing to do with our internal networks. You see, even if we run out of public IPv4 addresses tomorrow, our internal networks at our companies are not going to have any impact. We can continue to run IPv4 inside the network for a long time to come, possibly forever and always, as long as we are comfortable using NAT technologies to translate the traffic down into IPv4 as it comes into us from the internet. We've all been using NAT in one semblance or another for almost as long as IPv4 has existed. So it is obviously something people are very comfortable with doing. Let me be clear, I'm not trying to convince you that sticking with IPv4 is the best way, is the way of the future. I'm just saying, I'm just laying out the facts, that for most organizations over the next number of years, this will simply be the truth. The reason I want to discuss IPv6 here is that eventually you will have to deal with it. And once you do, you'll actually get excited about it. There are some huge advantages that IPv6 has over IPv4, namely the enormous amount of IP addresses that you can contain within a single network. Network teams in companies around the world struggle every day with the need to build more and more IPv6 networks and tie them together. Think about it, there are many companies now with employee counts in excess of 10,000. Some have many, many times that number. In today's technology world, everyone needs technology and data access. Data is the new currency. Most users now also have at least 2 physical devices they utilize for work, sometimes more than that, a laptop and a tablet, or a laptop and a cell phone, or a desktop and a laptop and a tablet. You get the idea. In the IPv4 world, where you are dealing with comparatively small IP address ranges, you have to get very creative with creating subnets in order to accommodate for all of these physical devices, which each need a unique IP address in order to communicate on the network. The biggest advantage to IPv6 is that it resolves all of the problems immediately and by default by providing the capability to have a huge multitude more IP addresses within a single network. How many more addresses are we talking about? Here is some comparison data to give you a little perspective. IPv4 address look like this: a 32-bit length address, 192.168.1.5. IPv6 address looks like this: a 128-bit length address, 1111:ab/00:AB00:123:4567:8901:ABCD. As you can see, the IPv4 address is much shorter, which obviously means there are fewer possibilities for unique IP addresses. When we set up IPv4 networks, subnetting is extremely important because it is what enables us to have more than one collection of IP addresses within the same network. In the most basic form of networking, where you set up some IP addresses and run a subnet mask of 255.255.255.0, which is very common on that subnet, you are limited to only 254 unique IP addresses. Some companies have thousands of different servers, let alone all of the client computers and devices that also need to connect to the network. Thankfully, we can build out many different subnets within a single IPv4 network in order to increase our usable IP address scope, but this takes careful planning and calculation of those subnets and address spaces, and is the reason that we rely on experienced network administrators to manage this part of the network for us. One invalid subnet configuration in our routing table can tank network traffic flow. Administration of subnets in an IPv4 network is not for the faint of heart. When we are talking about IPv6 addressing, the sky almost seems to be the limit. If you were to calculate out all of the unique IPv6 addresses available in that 128-bit space as shown earlier, you would find that there are more than 340 undecimal addresses available to create. In other words, 340 trillion addresses. This is the number being touted out there about how many available addresses there are on the internet, but what does that mean for our internal networks? To discuss the number of addresses we would have inside a typical internal network running IPv6, let's first step back and look at the address itself. The address I showed you earlier is just something I made up, but we will break down the parts of it here. 1111 colon AABB colon CCDD colon AB00 colon 0123 colon 4567 colon 8901 colon ABCD compared to 192.168.1.5. This thing looks like a monstrosity. That is because we are generally not very used to dealing with hexadecimal, but that is all we have here. It is just a different way of looking at data. As we already mentioned, this is a 128-bit address since it is broken up into 8 different sections. Each section being separated by a colon is made up of 16 bits. It is generally the case that companies would dedicate a section of this address as an organizational prefix, something that would be the same across all of their networks and devices. Let's say that the first 48 bits are the first 3 sets of hex, then the 4th set of information. The next 16 bits can be our subnet ID. This gives us the flexibility of still having multiple different subnets if we desire in the future by using multiple numbers here as the subnet ID. After deciding the first half of the address, we now have the latter half to work with, the last 64 bits. These we can leave for device IDs. This part of the address will be different for every device on the network and will define the individual static IPv6 addresses that will be used for communication. Let's lay it all out there. We will take the example address from the previous page and break it out into the following. Organizational prefix 1111 colon AABB colon CCDD colon AB00 colon 0123 colon 4567 colon 8901 colon ABCD 1111 colon AABB colon CCDD is the organizational prefix. Subnet 1111 colon AABB colon CCDD colon AB00 colon 0123 colon 4567 colon 8901 colon ABCD. AB00 is the subnet ID. Device IDs 1111 colon AABB colon CCDD colon AB00 colon 0123 colon 4567 colon 8901 colon ABCD. 0123 colon 4567 colon 8901 colon ABCD is the unique device ID. How many devices can we have in our network with an IP schema like this? Well, even in our example where we only allocated one 16-bit section for subnetting and 64 bits for the actual IP address, that would provide us with the capability to have more than 65,000 subnets and quintillions of unique device IDs in our IP range. If we stick with the aforementioned and use just a single subnet to contain all of our machines, then the first half of our address will always be the same, making these long addresses much easier to remember and deal with. It is surprising how quickly you will get used to seeing these large hex numbers in your environment, but even though you will start to recognize them, you will still probably are not going to quickly jump into servers or computers in your network anymore by using the static IP address. I know a lot of us are still in the habit of just saying, I need to quick jump into my web server. I'll just RDP into 192.168.1.5, just the time that it takes to type out these IPv6 addresses. Even if you remember them, isn't generally worth it. IPv6 will bring it with a much larger reliance on DHCP and DNS to make it more usable. Now that we understand what sections of the addresses are going to be used for what purposes, how do we go about assigning the individual device ID numbers for all of the computers and servers and other devices on our network? You could start with number 1 and go up from there. Another idea that I recently watched someone use is to calculate out the old IPv4 address into hex and use this as the last 32 bits of the address. If you open up the Windows calculator on your computer, drop down menu and change it into the programmer mode. This is a quick and easy tool that you can use to convert decimal into hexadecimal and vice versa. Let's take the example of my web server that is running on 192.168.1.5. I want to implement IPv6 inside my network, and I want my server's IPv6 address to reflect the original IPv4 address in the device ID section of the new address. In my calculator, if I type in 192 and then click on hex, it will show me the corresponding hexadecimal to the decimal of 192. If I can do that with each of the octets in my IPv4 address, you will see that 192 equals C0, 168 equals A8, 1 equals 01, 5 equals 05. So my 192.168.1.5 factors out as C0, A8 colon 0105. I can now utilize that in combination with my organizational prefix and my subnet ID to create a static IPv6 address for my web server. 1111 colon AABB colon CCDD colon 0001 colon 0000 colon 0000 colon C0A8 colon 0105. You'll notice in the preceding IPv6 address that I input the hex for the device ID at the end, but I also made a couple of other changes. Since we are leaving the last 64 bits available for the device ID, but my old IPv4 address only consumes 32 bits, I am left with the 32 bits in the middle. It would be kind of weird to have data in there which didn't mean anything to me. So I simply made it all zeros to simplify my addressing scheme. In addition to that change, I also adjusted my subnet ID to be the number 1, since this is the first subnet in my network. Our new addressing is starting to look a little cleaner and makes more sense now that we see this new address for our web server laid out. I can see that there are some additional cleanup tasks we can perform on the address in order to make it look even better. Right now, the address listed earlier is 100% accurate. I could plug this IP address into the NIC properties of my web server and it would work. However, there are a whole lot of zeros in my address, and it isn't necessarily that I keep them all. Any time you have unnecessary zeros within a 16-bit segment that are preceding the actual number, they can simply be removed. For example, our subnet ID and the first 32 bits of our device ID have a lot of unnecessary zeros. So I can consolidate the address down to this: 1111:CCDD:1:0:C0:A8:0:105. Then, to take it even a step further, anytime you have a full 16-bit sections that comprise entirely zeros, they can be fully consolidated into a double colon. So the first 32 bits of my device ID that are all zeros, I can replace with the double colon followed. The following is fully written out address and the consolidated address. These numbers look quite different. My consolidated address is much easier on the eyes, but from a technology perspective, they are exactly the same. 1111:00:00:00:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:5. In fact, it is even possible if you're setting up a lab or wanting to quickly test IPv6 that you could use addresses as simple as something like the following example. The two addresses that I will show you here are exactly the same: 1:1:1:1:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:0:1. Tip: it is important to note that you can use a double colon one time within an IP address. If you had two places where it could be applicable within the same address, you can only implement it in one of those places, and you will have to spell out the zeros in the other place. With the information provided here, you should have enough to put together your own semblance of IPv6 and start issuing some IPv6 addresses to computers or servers in your network. There is so much more that can be learned on this subject that a full book could be written, and indeed multiple ones have been. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing, and subscribing. Thank you.